Hello, in our lesson today, let us discuss unphased theorem. In quantum mechanics, particles are represented by wave packets. It is reasonable to expect the motion of the wave packet to agree with the motion of the corresponding classical point particle whenever the potential energy changes by a small amount, negligible amount over the dimensions of the packet. What are position and momentum of a packet? If we mean by position and momentum expectation values of these operators, then we can show that classical and quantum motions agree. And this was shown by Paul Ehrenfest in this paper, Zeitschrift für Physics, volume 45, page 455, 1927. And what he showed is that if we take the time derivative of the expectation value of X operator and multiply that with mass, we get the expectation value of momentum operator. And on the other hand, if we take the expectation value of momentum operator and take the time derivative, we get the expectation value of force, or minus expectation value of del V del X, where V is the potential. Now, what is expectation value of X operator? This is the definition: integral minus infinity plus infinity psi star x, X operator psi dx. Here we are working in the Schrodinger picture. So the operators are time independent, but states are time dependent. So we are working in Schrodinger picture where states are time dependent, but operators are time independent. So if we take the time derivative d dt of the expectation value of X operator, then we will get d dt of expectation value of the X operator is equal to minus infinity to plus infinity, and then d psi star dt X operator psi plus psi star X operator d psi dt dx. We don't get the term d dt of the X operator because the X operator is time independent. So that means we get d dt of the expectation value of X operator, and we can replace d rho dt with del x of jx. That is d rho dt plus del jx del x equal to 0. Then we get a minus integral minus plus infinity x del jx del x dx. Now we can do this integral. When we do this integral, we get two terms. X is the first term. It contains jx, and the limits are minus infinity to plus infinity. So see, in both minus infinity plus infinity, jx vanishes. That means the first term is 0. The second term is plus m integral minus infinity plus infinity jx dx. Now we can substitute the value of jx from here. IH cross by 2m psi del psi star del x minus psi star del psi del x. If we substitute, then we get two integrals from here. This term here will give two terms. What are the two terms? The two terms are this: psi del psi star del x dx and psi star del psi del x dx. And if we integrate this, we will get this. So finally, what we get is m d dt of the expectation value of X operator is twice psi star del psi del x dx integral minus infinity plus infinity dx. Because integrating one term, we have got the other term. And these two has got cancelled, these two with this two. Then we get psi star minus IH cross del x psi dx. And this is momentum operator. Then we get m multiplied by d dt of the expectation value of the position operator is the expectation value of the momentum operator. So this is analogous to the classical equation, mass into velocity equal to momentum. Next, we look at the time derivative of the expectation value of the momentum operator. This is minus IH cross d dt, And then psi star del del x, psi, because the momentum operator will have minus IH cross del del x. So we can take out minus IH cross outside the integral. Then we get ddt, integral minus infinity plus infinity, psi star del psi del x dx. Now this ddt can be taken inside because this is the x integral. So we take the ddt from here. We take the ddt and take it inside the integral. And then we get these terms, two terms. Psi star del del x del psi del t dx plus del psi star del t del psi del x dx. Now this term and this term can be replaced by the time-dependent Schrödinger equation, TDS. This is the time-dependent Schrödinger equation, which gives us del psi del t and del psi star del t. Thus we substitute del psi del t is this time-dependent Schrödinger equation, and del psi star del t, we take the complex conjugate of both sides, then we get del psi star del t, and then we substitute it in equation 4. Then we get two terms, term 1 and term 2. So this term 1 does not contain v, term 2 contains v. It is easy to see because del psi del t will have two terms. One, this term does not contain v, this term contains v. So when we insert it here, we get two terms, one from here, one from here. Again, del psi star del t contains two terms, one does not have v, another has v. So if we insert this here, then we get two terms, one which does not contain v and another which contains v. So finally we have two terms, term 1 and term 2, and we can evaluate term 1 and term 2 by just doing the integration. So term 1, psi star, this third derivative of psi, this is second derivative of psi star. Okay, so these are the two terms which does not contain v, and we simplify these two terms as this del del x of psi star del square psi del x square minus del psi del x del psi star del x dx. I will give this PDF in the description box, so you can really check it, how to go from this step to this step. You can go also the other side. You take this derivative, we will get these two integrals. So when we integrate, then we get this portion, and then we have to substitute the limit minus infinity plus infinity. But minus infinity plus infinity, psi is 0, psi star is 0, del psi del x is 0. So after substituting limits, we get it vanish. So the term 1 will vanish. What about term 2? Term 2 has two terms, but the second term, if we take the derivative, we'll get further two terms. Okay, so psi star del v del x psi dx. One term will get cancelled with this, and the second term will be psi star del v del x psi dx. So that will be expectation value of del v del x with minus sign. So that means ddt of the expectation value of momentum operator is equal to minus expectation value of del v del x, which is expectation value of force. So we can write it as expectation value of force. So that is analogous to the Newton's second law, which is rate of change of momentum is equal to force. But we are getting it in quantum mechanics, the Newton's second law, but we had to take the expectation values of operators. So in classical mechanics and quantum mechanics, they do agree so far as we take the expectation values of operators. The measured values or the eigenvalues, that is the individual measurements in quantum mechanics, the individual eigenvalues fluctuate around their expectation values. These fluctuations are also known as quantum fluctuations. Korn-Fer's theorem provides a bridge between quantum and classical mechanics. So I suppose this was very interesting, how to bridge between quantum mechanics and classical mechanics. And thank you for watching.